Okay, hello everyone. Thanks, Luca, for the introduction. I hope now that we managed to get all the to manage all the technical stuff, and you actually see my presentation and not whatever screen. So otherwise, I assume that everything is fine. Otherwise, please just interrupt me.
Yeah, it's fine. It's fine.
Good. Okay. So during my PhD, my focus was to apply clumped isotope thermometry and uranium lead dating of carbonates for various applications in stratigraphy, diagenesis, and geodynamics. So it was not that easy to decide what I should present you today, because it has been several projects, and I just tried to focus on two of them. Maybe it's only going to be one because of the time. I don't have that much time, I think. So I will see when I've just through with the first application, we check on time, and I can then go to the other one, or we leave it like that. So the approach of using diagenetic carbonates. So diagenetic carbonates form in a very wide variety of different diagenetic settings. They form due different processes, and also they form during different points in time in the lifespan of a sedimentary basin. So every time in the history of a basin, which is shown here with this gray line here, that's just an example. At each time they form, they record the temperature, they record the composition of the fluid during precipitation, and they also record an age. So if we have the tools to assess these temperature data, the fluids, composition, and the age, we get actually discrete points in time. Now, if these cements are preserved and datable, they allow to reconstruct the evolution of temperature or the evolution of fluids during the lifespan of a sedimentary basin. Now, the more complex the diagenetic history is, so the more diagenetic phases that we form, and the more tectonism taking place throughout the geological history of a basin, the more of these points we get, and the higher is going to be the resolution of the thermal and burial history of that sedimentary basin. And that's also an important advantage of diagenetic carbonates compared to other thermochronometers such as apatite, fission tracks, or reginite reflectance, because these values here, there are discrete points in times, whereas the other ones, they give you more of an integrated signal. Okay, let me give you some introduction to the methodology. First, how do we reconstruct absolute ages with uranium lead dating? We do it with laser ablation ICP-MS dating. That means we have a laser coupled to a mass spectrometer, and with that laser, we shoot small holes into the cement that we want to date. These you can see here. On the left side, just a normal thin section photography, and on the right side under cathodoluminescence light. So with this laser, we shoot many points of a cement. And on this point, then we measure the 207 lead to 206 lead isotopic ratio and the 238 uranium to 206 lead ratio. To quickly go back to how do uranium lead isotopes actually record an age. So we measure actually two decay systems, and the theory behind that is that we have a total isotope today, that's 206 and 207, and these two are actually formed by the nuclear decay from 238 uranium to 206 lead, and from 235 uranium to 207 lead. Now this lead composition here, it's actually it's composed of two separate pools. So the first one is the initial isotope that is present at the dated event. So we call that the initial lead or the common lead. And the other pool is the radiogenic daughter isotope that is produced since the dated event. So what we measure in the carbonate, this the 206 and 207 lead, is actually always a mixture between this initial isotope that is present at the dated event and the radiogenic daughter that has evolved since the deposition, so through time since the dated event. Okay, we then plot these isotope ratios in a so-called Terra-Wasserberg diagram. The most important features here are actually this line here, the brown line, which shows you the evolution of 207 as 206 and 238, 206 isotopic ratios. And so these points that we got here, actually then we plot here. And if the sample is datable and if it gives a good age, you have a large spread of different composition in 207, 206, and 238, 206. And then we draw a regression, an isochron, and we get two end members. The first end member here, up here, that's the initial lead composition, which is again isotopic composition of the lead that was present at the time of precipitation. Here we assume that there is no, or we derive the components of 0 radiogenic lead. And the other thing that we get, and that's more important for us here, is the lower intercept age. That gives us the time that elapsed since the dated event. So actually the time that is needed for the isotopic ratios to derive the isotopic ratio down here. Here we assume that at the time of the precipitation, no initial lead, common lead, was present. Okay, so we basically always work with these lower intercept ages. The procedure that we do at ETH for laser ablation ICP-MS is that we first do a lot of CL microscopy, and with that we try to identify different generations of cements. Sometimes you don't see this under normal microscopy, but then under cathodoluminescence you see different luminosities and so on. Because it's important that you don't mix them. It's very easily, and it happens fast, that you actually start mixing H's, which then of course is going to bias your uranium lead H's. Then what we do during the session, we decide which ones of these cements are suitable for dating. So this pre-screening is that we just take the sample and we actually ablate some test holes, which then we can decide based on that if we have enough uranium to try dating it, or if it's basically hopeless. In the second step, then we choose crater size and repetition rates, also based on the uranium content. So if we have low uranium contents, we do basically we shoot bigger holes to ablate more material to get enough signal. Anyway, if you do that, it's very important to keep the aspect ratios, the ratios between the diameter and the depth of the ablation pit constant. Otherwise, if this geometry is going to be like more deepened, you will have a systematic age offset towards older ages. So basically, these observations you can look up in the paper of Marcel Guillon. What we do then is we do a data reduction, including correction for drift, using NIST 614, glass standard for mass bias, and finally the correction for matrix effects on 238, 206, which is caused by the carbonate matrix effects. And therefore we use WC1, which is the carbonate standards actually all labs work with. Okay, after the session then during the session actually, we also measured 3 different in-house standards, JT, ASH15D, and PDF9B, to assess the long-term accuracy and reproducibility of the H's that we get. And finally, actually after the measurements, we do CL microscopy again to really check if we caught all the carbonate phases, and we identify misplaced and defective ablation points, which we then remove from the data set. Okay, clumped isotope thermometry. To give you some theory on that, what we do there is actually that we measure the commonness of CO2 that contains both of the heavy isotopes, Mese 47 compared to commonness of CO2 with only one or none of the heavy isotopes. So we focus on Mese 47. Here you can see that's the so-called isotopolog that contains both 18O and 13C in the same molecule, while the others, masses 46, 45, and 44, they contain either none or only one of the two isotopes. So there is a tendency that 13C and 18O kind of like to bond together instead of bonding with a light isotope. And this effect is larger the cooler the precipitation temperature is. So this whole thing with Mese 47 actually and clumped isotope thermometer has this delta 47 notation, which is defined by the ratio of 47 compared to what you measure compared to the one that you would expect if 13C and 18O actually were randomly distributed, compared to the isotopolog with none of the heavy isotopes. Anyway, that's not too important for you. Important is clumped isotopes is always, in my case at least, delta 47. So what we do, we get the carbonate, we dissolve it in, we digest it in phosphoric acid, and from that then we derive the CO2, we purify it, and then we ionize it and then measure the clumped isotope composition by IRMS. Okay, importantly, delta 47 is independent from delta 18O and delta 13C, and it is only dependent on the formation temperature. That means by measuring delta 47, we derive the temperature directly, and with that temperature then we can calculate the oxygen isotope composition of the precipitating fluid. And here the cool thing is that we don't need to make any assumptions. So that's the advantage compared to oxygen isotope thermometry, where when you want to calculate the temperature, you need to assume a certain isotope composition of the fluid, or the other way around, if you want to calculate the oxygen isotope composition of the precipitating fluid, you need to make assumptions about the temperature. Okay, so far so good. When it comes to deep burial settings, there is one important obstacle that has been limiting the use of clumped isotope thermometry, and that is called solid state reordering. And solid state reordering takes place in at high temperatures, at temperatures that are high enough to, like they are higher than 100 degrees, more or less. Also, that depends on how long it was heated above 100 degrees, or if it was, you know, for a short time hotter. Anyway, the important thing is here, just as a rule of thumb, if you reach temperatures above 100 degrees, you might have a problem with solid state reordering. Now, what is it? What is the effect of solid state reordering on the clumped isotope temperature? So the clumped isotope signal that is shown here is preserved if the carbonate, and this is indicated with this shell here, remains below the temperature limit for the preservation of delta 47, which again is thought to be in the range of 100 degrees. Okay, if you don't reach this temperature limit, the clumped isotope composition, the clumped temperature that originally was recorded during the time of precipitation, let's say, for example, 25 degrees for this shell here, after the whole burial history of whatever, how long it took, let's say 200 million years, when you measure that again today, you will still retrieve this correct original formation temperature. However, in the other case, if the burial temperature exceeded here this temperature limit for the preservation of the clumped isotope signal, if you went above that, the delta 47 of your fossil will shift, and the temperature that is recorded by that gel, the temperature that you measure today, is higher than the initial temperature. So this results in a so-called apparent formation temperature. And the bad thing about reordering is, or what it makes it hard to see if something is reordered or not, is that there is no structural geochemical change that would point toward that. So in contrast, if you have recrystallization, you will change the structure or the crystal size of the carbonate. Or if you crystallize under open system conditions, then you will even change the oxygen and carbon isotopes, or manganese, iron, whatever. In case of reordering, you don't see that. There is no way to actually prove solid-state reordering. It's just, you know that it's there if you can include all the other processes. Okay, on a molecular level, what actually is happening is that when you're experiencing temperatures that are high enough, then the activation energy barrier for oxygen and carbon isotope exchange within the mineral lattice will be overcome, and then the molecules will exchange oxygen isotopes. And if that is happening, of course, you will lose 13C, 18O bonds, and the clumped isotope temperature will increase. Okay. So what is the effect of that or what is the effect and what is the problem with that for burial histories? So we go back to this sample that we had, or so this burial history here, where you have diagenetic carbonates that formed during different times. And what will happen is that all the carbonate phases that formed prior to this time of heating, where actually you have solid-state reordering, is that these temperatures will be higher. So for example, in the beginning, instead of 30 degrees, which is the true formation temperature, the apparent temperature that you measure today is 50 degrees. Or here, if the original temperature was 70 degrees, today you will measure 80. In contrast, after the steep burial here, these temperatures are still correct. Okay, so importantly, that all phases prior to a deep burial event or a phase of deep burial with temperatures above the limit of the preservation limit of delta 47 might be biased. Okay, so there are different factors that influence solid-state reordering. The first one is the thermal history. So the more heating or the longer heating above this preservation limit, the higher the change in 47 temperature is going to be. Then secondly, the formation temperature. So the lower formation temperature, the more you will change the clumped isotope temperature during the reordering. So for example, in this case here, a phase that crystallized originally at 20 degrees will at 125 degrees experience a change of plus 32 degrees, and a phase that here precipitated at 60 degrees will only change by 16 degrees. So it's a compression effect. And the third effect is mineralogy. Calcite, dolomite, aragonite, those are the minerals that have been examined so far. And as we know is that dolomite reorders is the most resistant against reordering, then calcite and aragonite is the most vulnerable. Okay, and what we during my PhD also found out is that the reordering is also faster for biogenic calcites than for abiotic calcites. So this means that for the same thermal history, fossils always will show higher apparent delta 47 temperatures than abiotic calcites. And it also means that if fossils then show no or only very little reordering, the delta 47 temperature of diagenetic carbonates are trustworthy. So we can use fossils in a burial history to check for solid state reordering. And I will come back to that at a later point. Okay, so the first application, and if I see the time, probably the only one today, is about constraining the burial history of the late Triassic to early Jurassic sediments in northern Switzerland. Here you can see the study site, which is here in the Tabular Jura of northern Switzerland, close to the today's margin of the Molas Basin. Here on the right side, you can see basically what happened during the last 2 million years, or the last 300 million years. So during the Mesozoic, there was differential subsidence at the continental margin of the Tethys Ocean. During Cretaceous, during Triassic to Cretaceous time, that leading to a first interval of deep burial during Cretaceous times. Then we basically don't know what happened because there is a huge hiatus. What we know though is there was a forebulge with crustal foreland uplift during Paleocene to Eocene actually. And because of this forebulge, the whole Cretaceous and also the uppermost Jurassic sediments are not preserved. For the Jurassic sediments, we actually know that there have been Jurassic sediments, young ones, but for the Cretaceous, it's actually not clear. Okay, so after this forebulge, then the Molas Basin as a flexure foreland basin evolved, starting in Oligocene times with deposition until more or less late Miocene. Before then, the Molas Basin actually was inversed and got eroded ever since. Okay, so basically, or important for the thermal history that I will present is we have 2 cycles of burial. First, burial due to ongoing sedimentation during the Mesozoic. We don't really know until when it lasted. Then a first cycle of erosion due to the forebulge, a second interval of burial because of the Molas, and then final exhumation. So the burial history is actually, for that project, I only worked on very few stratigraphic horizons. It's mostly the Begingen member, which is early Jurassic Sinemurian limestone. So the stratigraphic age is late Tertian to late Sinemurian, which is more or less 290 million years ago. Here on the right side, you can see a picture from the outcrop. So it's one of the few competent massive limestones that is embedded in more shaly and marly stratigraphies. And why I chose the Begingen member is that there is just a whole lot going on. So there are a lot of different diagenetic phases, different veins. And as I said in the beginning, the more complex the diagenetic history and the more tectonic events that created the pore space for fluid flow and precipitation of carbonate cements, the higher the resolution of the burial history. So this site was just very good because we had excellent sampling conditions, and in the rocks are just a lot of different diagenetic phases. Okay, here's some samples of what I looked at. So here that's an ammonite chamber of an ammonite, you can still see the ammonite septum, and the open space is filled with 2 generations of cements. First, a calcite cement, and in the interior then a saddle dolomite. Then aragonite replacement cements. These shells here were originally composed of aragonite, and then during diagenesis, this aragonite was replaced by calcite. Then we have different generations of veins with tons of cross-cutting relationships. We have calcite veins, then we have calcite veins with an inner generation, again, of saddle dolomite. And finally, we have very late phases, anhydrite replacing calcite cements. So these nodules here, those were originally filled with anhydrite, and then during exhumation and the influence of water, fluid flow, this anhydrite was dissolved, and these meteoric calcite cements were precipitated. And finally, also flowstones composed of aragonite and calcite. Okay, so in total, we have 12 generations of different cements that we could separate based on relative age constraints, based on uranium lead dating, based on cathodoluminescence, and based on clumped isotopes. So on the left side here, you see a plot showing the composition, the oxygenizing composition of the precipitating fluid, and on the x-axis, the delta 47 temperature. And here, actually, with different colors, indicated the different samples that we analyzed. So all the analyzed carbonates group in discrete fields that reflect different diagenetic environments and temperatures between 10 and 120 degrees. So that's the cold end members, the hot end members, and fluid compositions between +3 and -10. So, and here it's important to understand that samples with low clumped isotope temperatures and a very meteoric fluid, they form more or less under meteoric conditions or under Earth surface conditions, while then in the high temperature regime and if with very rock buffered fluid compositions, you are more like in a deep burial environment. Okay, so in this plot, you can see actually the data, the clumped isotope data plotted against the uranium lead ages. In the upper box, that's temperature, and in the lower box, you see the delta 18O fluid composition. Again, for the different diagenetic phases that we analyzed. And here the phases with the black spot, that's actually that's a sample that was dated with uranium lead. Okay. Also important is we are actually not the first ones to try to reconstruct the burial history of northern Switzerland. There is this work by Mazurek and others from 2006, and they derived this this temperature evolution model for the base of the sediment and for the base of the Middle Jurassic. And that is based on inverse thermal modeling of apatite fission track, vitrinite reflectance, and biomarker isolation data. But as I said, that's all integrated temperature signals, and we try to constrain that burial history now with discrete points in time. Okay, so let me walk you through that. So the first phase that we see is early burial, and this phase is constrained by pore filling cements in open voids of fossils, for example ammonites, but also in brachiopods, and aragonite replacing calcite cements. So all diagenetic phases that we know, they take place very early in early burial. And what we see here is actually that the uranium lead ages agree very well with the stratigraphic age of the bagging member, which is 219 million years. And the temperatures are more or less of what you would expect for early burial, temperatures between 30 and 40 degrees. We see, though, one or two temperatures that are too high, and this can be explained by later stage closed system recrystallization. That means, so if you recrystallize a cement under closed system conditions, then it will record a new temperature, but you will keep the uranium lead age because you're not changing the isotopic composition of uranium and lead. Okay, so that is a potential explanation for these two here. And also what we see here is that normally the isotope, the water composition is somewhere around seawater to slightly modified seawater. But in two cases of pore field cements, it's considerably lower than we would expect. And this here also fits actually quite well with or can be explained by temporary emergence above the sea level and freshwater inflow. And this has been documented for this bagging member. So it is known to actually constantly be emerged above the sea level, then again transgression, go below it, and so on. Okay, so generally here this early burial phase fits well, more or less what you would expect. And also it shows you actually the correct uranium lead ages of these early cements show you that you can use uranium lead dating of early diagenetic phases to constrain the depositional age of a horizon. Now that is interesting if you want to go back in deep time where you have no biostratigraphy, for example. Just if you have ever the problem of not knowing how old a stratigraphic horizon is, if you manage to date early diagenetic cements, they will give you the correct age, or they have the potential to give you the correct depositional age. Okay, then the second phase is deep burial. Here we see a temperature increase from more like seawater temperatures, early burial temperatures, to up to 95 degrees at 120 million years. These data here we just leave away for the moment. I come back to that. So what we see for this 95 degrees at 120 million years ago, we see a fluid that is only 0.8. Now we measured the host rock on 25 samples, and then we tried, or what we actually did, we calculated what would be the equilibrium composition of the fluid. So if a fluid was in full equilibrium with the host rock, this fluid would have a delta 18O water of +9. So more than 8 per mil more heavy than actually what we see. And this is actually not clear what is the reason for this. It could be that it's rapid infiltration of seawater and only partial equilibration of that 18O, or it could be mixing with a fluid depleted in delta 18O. So importantly is, at that point during Cretaceous, there, as far as it is known, there was a sea, Cretaceous sea. So the isotope composition of the fluid that was infiltrating was somewhere between -1 and 0. Okay, so it is still enigmatic why this oxygen isotope composition is that low. Then going to the next more or less enigmatic thing is this phase of hyperthermalism. We have this phase of saddle dolomite that we find in veins and as late generation pore field cements, and those just completely follow what is expected from vitrinite reflectance data from apatite fission tracks, biomarker isomerization, and actually also from stratigraphic constraints. So this is rather unusual. We have uranium lead age of 147 plus 10 million years that we measured on 4 different samples. So this is a weighted average of these four H's. And we have a Taylor 47 temperature of 117 degrees and a fluid of plus 2.7. Interestingly, we have the youngest preserved sediments on top of that that are 150 million years old. So, and 155 million years, it's almost within error of the uranium lead age of these cements. And these sediments are only 500 meters above the beginning member. So that means that at these settled dolomites formed approximately under 500 to maybe 1,000 meters of sediments, and still getting these very high temperatures. Okay, that means if we assume that the stratigraphic age and the settled dolomite formed during the same time, so they are within air, and if we work with that, then we derive a geothermal gradient of 170 degrees, which is of course super high. And then if we say, okay, within the 8 million years that we don't have any stratigraphic constraints, so between 155 and 147 million years, we just say that during that times another 500 meters of sediments were deposited, then we still get a geothermal gradient of 9 degrees per kilometer. So we don't know what actually happened. Clearly, it cannot be burial. So there must be something going on, like a high heat flow. Then the other question then, or the other idea is, okay, then it must be deep fluid convection. It's what you would expect, right? Temperatures that high, they must be just being the result of a deep fluid convection. Then the problem is there we have only 1,300 meters towards the crystalline basement, which we regard as impermeable, and we don't see a fracture network in the sediments below the beginning member. Okay, so it cannot really be, you know, like a channelized fluid, but I don't know, maybe it is diffusive. So we just want to check, is there a hot fluid sourcing from the crystalline basement? And for that, we analyzed strontium isotopes, which you can see here. So the idea is, do we have any constraints that there was fluid flow with the signature from the basement, just a fluid flow from the basement into the lower Jurassic horizon? Do we have anything like that or not? And if we have this, we would see this probably in strontium isotopes, because the crystalline basement has a much more radiogenic isotope signature than Jurassic seawater. And interestingly, we don't see that at all. So settled dolomites, the phase that formed during this hyperthermal phase, it is completely, it has the signature of the Jurassic Cretaceous seawater. That means that we have no indication for fluid sourcing from the basement. That can be because either the fluid flow was restricted in the Jurassic units, or the 87-86 strontium ratio is just buffered by the limestones that contain much more strontium than the crystalline basement. Okay, so also if the latter is the case, we can argue that this thermal equilibration takes place much faster than the isotopic equilibration of 87 and 86. That means then that this temperature actually indeed reflect ambient temperatures rather than just a fast cross-formational deep fluid convection. Okay, so the strontium isotope don't say us anything about the source in that case, or it doesn't tell us that it's sourced from the crystalline basement, but it's telling us that it was in thermal equilibrium with the host rock. So this 117 degrees, they were ambient temperatures, and it was not just restricted into some channels from, from in the network of fractures. Okay, at that point, I want to come back to what I stated previously, that biogenic calcite shows faster solid-state reordering compared to abiotic calcite. As I said, for the same burial history, fossils always will show higher apparent delta 740 temperatures than abiotic calcite. And if fossils show no or only very little reordering, the temperatures of diagenetic carbonates are trustworthy. So what we basically did in this other project where I show this picture here, we did heating experiments on belemnite calcite. That means we just took a piece of pristine, well-preserved belemnite. We put it in the oven at, in this case, 420 degrees. And then we just took, after 1 hour, 10 hours, 20 hours, 50 hours, 100 hours, we always took a sample out and measured the delta 47, which then is showing the decrease. And if we compare this belemnite calcite, which is these orange circles here, with all other calcites that have been tested previously and that we tested, these are optical calcite. This is a spar calcite. We see that belemnite calcite is faster than the other ones. Okay, so in this project, we also derived kinetic parameters, which are going to be important in the next slides. Okay, so here, back to the Begingen member. Besides the diagenetic carbonates, we also measured fossils. And we measured a bivalve, plagiostoma it's called. We measured belemnites and brachiopods. What we derive is clumped isotope temperatures of pooled together 39 degrees for brachiopods, only 32 degrees for the plagiostoma, and above 50 degrees for belemnites. Okay, if we compare, when we compare them, this clumped isotope temperatures with delta 18O temperatures, importantly, these temperatures, the delta 18O temperatures, they're not influenced by solid state reordering, then we can estimate the amount of reordering. Okay, so if we assume a water composition of the early Jurassic seawater of -1, that means, or -1 to 0, and that means during that times there was no ice sheets on the poles. That's why the whole ocean was more depleted in 18O. And then on the other hand, it was quite low latitude, so some evaporation. If we work then with delta 18O of around -1 to +1, we see that the reordering is around 10 degrees for brachiopods, no for the plagiostoma, and around 25 degrees for the belemnites. Okay. With our heating experiments, we then showed that belemnite always reorders faster than all other previously analyzed calcites, including brachiopod calcite. So we can use fossils and especially belemnites as worst case scenarios for change in delta 47 temperature of the diagenetic cements. That means if we see for brachiopod calcites and this plagiostoma, which are more similar to abiotic calcites than belemnites, then we see that the delta 47 temperatures of the diagenetic phases are actually trustworthy. And in a second step, we can then use the partially reordered delta 47 temperature of the belemnites to estimate the duration of these hyperthermal events. Okay, so here again, that's the phases, the different dolomites that we dated during this hyperthermal phase. We have 4 ages between 151 million years and 135 million years. And now we have two options to interpret these ages. Maybe it's just analytical error. That means they are actually all within error of each other. That means this would be a short-lived event, let's say 1 million years. The other way, it's possible that actually it was more long-lived. And the difference that we see here are actually not just analytical error, they're showing a true difference in age. Okay, so that question remained open. Now what we can do, we can run reordering models that are calibrated with these belemnite specific kinetic parameters and predict the apparent delta 40 temperatures for the different scenarios of the duration of this hydrothermalism. So, and that's what we do here actually. So we have two models. I'm not going to go into details what they are. Ones here, A and B, they show the barrel history in black with a very short-lived 1 million year hyperthermal phase, and C and D here, they show the barrel history with a long 16 million years phase of hyperthermalism. Okay, and what we see actually, that these models predictions show that the, that the 47 temperature of the belemnite that we measured here today, is 53 degrees, they are compatible with a low or a short lasting phase of hyperthermalism of 1 million years, or maybe 2 or 3, but they are not really compatible with long hyperthermalism of 16 million years or even longer. That means we can use this partial reordered belemnite to actually constrain duration and the maximum and the peak temperatures of deep burial. And this is a very good alternative, or it's a very good add-on to complement the delta 47 temperature history that was derived on diagenetic phases. That's, I think, something that is going to be more important in the future, that we also start using partially reordered fossils to then see what were the maximal barrier temperatures and for how long did they last. So this is like an additional constraint to diagenetic phases. Okay, so the last phase that we see here is exhumation. We see a decrease in temperature from 45, from above 120 degrees to above to 45 degrees at 30 million years, and finally then even more decrease towards like 10 degrees. So this is actually a mega trend of exhumation that we see starting in the Cretaceous and lasting until today. We also see that this mega trend of exhumation comes with a decrease of 12 per mil in fluid. So here we were still not kind of rock buffered enough of what we would expect, but we had fluids of around 3 per mil, and then we see, because of this exhumation, a decrease in the fluid, more influence of meteoric fluids to subrecent conditions today. Yeah, so what we would need more to constrain the burial history during the Cretaceous is actually more data, because we have these weird hot phases that don't really add up in terms of geothermal gradients. We know there must have been hypothermal events, but it's very hard to calculate actually what the source of the heat was and how much of overlaying sediments of the Cretaceous was eroded since then. Okay, so that would be the second application, but I don't think I have the time for it. So I just refer to, oops, goes too fast, sorry. Just refer to these two papers. One that I published a year ago in Tectonics. It's where we constrained the tectonic activity of the alpine foreland, once in the basal décollement and together with Luca, but I think he can tell you more about that Also different tectonic pulses more in the Western Jura. Okay, yeah, so that's from my side. Happy to take any questions.
Thanks a lot, Nathan, for the nice presentation. But if you want to give us a shot about the second application, if you can do in 5 minutes, we can do.
Okay, yeah, happy
Maybe,
to.
Yeah.
So I'm kind of rushing that through. If you want to have it in detail, you can go and look for the publications.
Yeah.
The formation of the Jura fold and thrust belt took place coupled to the evolution of the Alp, the late stage evolution. It occurred due to the distant push, so-called distant push, and basically shortening propagated to the foreland in a thin skin manner along a shallow dipping thrust décollement, which you can see here. And the problem is was so far, that there was no direct age and temperature data for thrusting along this basal décollement. And we wanted to change that. So normally, the problem is with the basal décollement, because it's composed of evaporites, is that all the veins that you find there are filled with anhydrite cements and no calcite. And the problem of anhydrite is that we cannot assess it with uranium light dating or clumped isotopes. So our approach was to analyze calcite mineralizations in fractures that are associated with the thrust folds located between the two deformation levels of the basal décollement, which you can see here. So these structures here, that's one of the thrusts that we analyzed. We analyzed the so-called Schaffisheim thrust, which is in the interior of the Molas basins, some 10 kilometers in front of the main thrust of the Jura Mountains. And then we also analyzed the same stratigraphic horizon here in the interior of the Jura Mountains, in the HB and AU thrusts. And in addition to that, two strike slip folds, the AK and AA. I spare you the names. Okay, so importantly, these structures that we analyzed, in case of Schaffisheim and HB and AU, they are secondary structures that actually branch off from the basal décollement, and therefore they reflect the timing as well as the burial conditions during tectonic activity of this basal décollement. So at Schaffisheim, okay, on the left side you see more or less a sketch of this Schaffisheim thrust. Here we have in blue color the mechanical basement, and here the décollement. And so what actually, that's also how they found this thrust. It is in a deep borehole, is you have a repetition of lithological units. So you have 1, 2, 3, and then this thrust fold, and above again 1, 2, 3. Here indicated with shown this repetition here. Okay. In this thrust fold, below this thrust fold, we have in the footwall a damage zone. We split this damage zone in an inner part with a fold fracture and in an outer part, which we call the outer damage zone. So in the outer damage zone, you still see the original stratigraphic layering, while in the fold fracture, this is all gone. So you have clasts that are rotated. So within this fold fracture in the footwall of the thrust, we see 4 populations of veins that we can take apart or keep apart based on structural relationships. So vein population 1 are thin veins that are cross-cut by vein population 2 veins and showing various dips. Then vein population 2 veins. In the outer zone, they are more shallow dipping to sub-horizontal, and in the fold fracture, they are truncated themselves. So actually, you can see this here. They are always not cutting through multiple clasts. They're always cut by the clasts. Okay. And then we have vein population 3, and those veins here, they cut through different clasts. So we know VP2, they are truncated at clast boundaries, so they predate thrust-related cataclases. And VP3, they cut through clasts, so we know that they form syn cataclases or post cataclases. And then vein population 4, it's subvertical orientations, and they cut through all other vein populations 1, 2, and 3. Okay, so we have good structural constraints on that, and we were able to date a lot of these veins, and we show that veins of vein population 1, the ones that were clearly pre-cataclasis, they show a weighted average age of 14.3 million years. Vein population 2 and vein population 3 veins, they are just on top of each other. That means the veins that formed prior to the thrust-related cataclasis formed at the same time as the ones that we know they formed syn or post-cataclasis. So that helps us to really constrain thrusting along this secondary thrust. And then we have younger ages of vein population 4 at around 8-9 million years. Okay. So that was that. These ages were all from the Schafisheim thrust, which is located more in the south. So that is expected to be a little bit older than the other ones. This is plotted here. That's the data from Schafisheim. And then we also analyzed these thrusts at HB, Habsburg, and AU, Asp, Uslimat. Those are the locations. And here we see ages between 12 million years and 4 million years. Okay. So in a nutshell, what we see is in Schafisheim with ages of 14.3 million years that are clearly related to this thrust, is that thrusting along the basal décollement was earlier active than it was commonly inferred for the Jura Mountains. We see that the deformation to tectonic activity of the basal décollement was not short-lived, but occurred over a time period of 10 million years, between 14.3 and 4.5 million years. And we see during that time that there was contemporaneous activity and maybe also interplay of thrust and strike slip faults in the Jura Mountains. Then what we also see, or we think we see it, but it's different to really put the finger on that, is that it seems that we see a younger onset of deformation in the Jura Mountains than in the northern Molas Basin, which you would expect because the foreland propagation, the foreland direct propagation of the deformation front. Anyway, the problem here is we don't have a lot of data points from different faults and thrusts, so we can't really say it for sure, but our data is in agreement with that, so we wouldn't see out of sequence behavior. So the last slide on that, what can we say about the burial conditions? So what we see, so that's the clumped isotope data. At Schafisheim, we see temperatures of 104 degrees throughout the whole phase of deformation. And in the Jura Mountains, we see at the same stratigraphic interval thrusting taking place at only 70 degrees, 73 degrees. Okay, so the cool thing here is that during the time period of roughly 12 million years and 9 million years, we have thrusting taking place at Schafisheim and in the Jura Mountains. That means we can now compare the burial conditions during the deformation in these two regions. Okay, so what we see here, actually, this 104 degrees, is that they indicate burial at 3 to 4.7 kilometers, and in the Jura Mountains during the same time only 2 kilometers of burial, which you would expect with the molar spacing. What you can see is actually at Schafisheim we have a fluid of +9, which is in complete equilibrium with the host rock, while in the Jura Mountains we have fluid compositions that are clearly meteoric influenced. That means that there was a hydrological connections to the surface, or at least shallow groundwater aquifers in the Jura Mountains. Okay, so here the clumped isotope data basically adds a lot of information about under what temperatures and under what burial conditions did the thrusting take place, and if there was connectivity to the Earth's surface or not. Okay, that was really much in a nutshell. So if you want to see more about that, you can find the papers. Thanks.